The first lesson of Unit 4 is an introduction to exponential functions. So what we're going to do is we're going to start by sketching the function f of x is equal to 2 to the power of x. So we've got a graph here, and we're going to sketch the graph of y is equal to f of x by completing the table of values below and then plotting that graph. So let's look at our table of values right here. If x is equal to -3, what would y be equal to? So let's go to the function here. If we insert -3 into the function, what would the value of the function be? So why don't we do a calculation to that effect? So f at -3 would be equal to 2 to the power of -3. We know that negative exponents cause us to take the reciprocal of the base. So I'm going to take the reciprocal of 2, 1 over 2, now raised to the power of 3. And when I evaluate that, I get 1 over 8. So the first value here is 1 over 8. Similarly, if I insert -2 into the function, I should get 1 over 4. Now what happens if I just insert -1 into the function? Well, f at -1 is equal to 2 to the power of -1. Well, that's just the reciprocal of the base, so 1/2. This right here is a bit of a special case. If I put in 0 into the function, I get 2 to the power of 0. And anything raised to the power of 0 is equal to 1. So I get 1. F at 1 will simply return the base of the function, so the base of this function, which is 2. And then inserting the rest of these values will give me the following. So 2 raised to the exponent of 2 is 4. 2 raised to the exponent of 3 is 8. And 2 raised to the exponent of 4 is 16. So this is my table of values for the function y is equal to the power of x, which is our exponential function. I'm now going to plot these values on the graph that's given. So if this is -1, this is -2, and this is -3, well, we evaluated when x is equal to -3 that I get 1 over 8. So that's quite small. We'll put that right down there. When x was equal to -2, it was 1/4. Again, pretty small. When x is equal to -1, it was half, so that one's a little easier to draw. Okay, and when x was equal to 0, I got exactly 1, right? Because again, anything raised to the exponent of 0 gives me 1. So my y-intercept there is going to be 1. When x was equal to 1, I got 2. When x was equal to 2, I achieved 4. And 3 gave me 8. Okay. And we can see as this moves on, if I was to do 4 as well, I would get 16, which is right here. So as you can see, the graph is growing exponentially. So I'm going to now connect these with a continuous line, or a continuous curve. Put my arrows on either side. And I'm going to examine my graph and answer the following questions below. The first question I'm asked is, would there be an asymptote in the above graph? Why or why not? And if so, what would be that asymptote? So when I look at this graph, it increases upwards and upwards and upwards, and it looks like it's going to keep going upwards as x progresses towards infinity. As x progresses towards negative infinity, my values are going to keep getting smaller and smaller. This is also seen in my table of values. As I get more and more negative, my values get increasingly smaller, right? Because the negative number here is forcing me to take a reciprocal of the base, which results in an increasingly smaller fraction. So the question is, these values, these y values, get increasingly smaller. Are they going to ever achieve 0? So will these fractions ever achieve 0? Well, they will not. So there will in fact be an asymptote. So yes, there will be an asymptote because as x approaches negative infinity, so as x gets smaller and rather more and more negative, the value of f of x gets very small. It approaches, but never reaches 0. So as a result, I will have an asymptote in here, and it will be for when y is equal to 0. Knowing that there's an asymptote in this graph, what I've done right here is I have plotted the asymptote and labeled it y is equal to 0 with a dotted line indicating that this graph will approach but will never achieve the value of 0 for y. And over here I have labeled the function right here, f of x is equal to 2x. So now I'm asked to state the domain and range of this function. Well, let's start with the domain. And I ask myself, what are all the possible values for x? Well, as I can see here, x will continue to get small, so x will approach negative infinity, and there's no restrictions, it can get smaller and smaller. And x can approach positive infinity and get larger and larger. So no restrictions on the x values. So I'll write, using my set notation, x is an element of real numbers. My range will have a different case. As we can see here, as x approaches positive infinity, my y values are going to get increasingly large. And in fact, they'll probably go up towards positive infinity as well. As x goes to negative infinity, my y values, as we saw before, are going to get increasingly smaller, but they will never approach 0. So what I have to do there is I write for my y values, y is an element of real numbers with the restriction that y must be greater than 0. Note, I say greater than and not greater than or equal to 0 because, as we said right here, the graph will never approach, or will never rather achieve 0. It approaches 0, but never achieves it. The final part of this page asks me to sketch the graphs of y is equal to 1/2 raised to the power of x, y is equal to 3 raised to the power of x, and y is equal to 1/3 raised to the power of x on the graph in a different color. And what we're going to do is we're going to compare the features of these three graphs with the graph that we've already plotted. I'd like to do a table of values for this first graph right here so we can see what's going on. But for the rest of these graphs, I'll simply use a graphing application to see what they look like. So I'm going to turn my page and create a table of values for this graph right here. Okay, so what I'll do is I'll start with x is equal to -3. So x is equal to -3 would mean when I insert -3 into this graph, I get 1/2 raised to the exponent of -3. Well, as you recall, the negative forces us to take the reciprocal of the base, which is 1/2. So the reciprocal of the base is going to be 2/1. Now raised to the exponent of 3, which is equal to 8. So my first point will be -3, 8. Doing the same for -2. 1/2 raised to the -2, well, that's simply going to be equal to 4, because the negative will cause me to take the reciprocal of 1/2, which will give me 2/1 raised to the exponent 2 is 4. -1 would be 2. 0, again, anything raised to the exponent 0 is simply 1. as I go into the positive values for x, 1/2 raised to the exponent 1, it's just 1/2, 2, 1/4, and 3, 1/8. So what I'm going to do now is I'm going to plot these values here, -3, 8, -2, 4, -1, 2, 0, 1, so on and so forth, on the graph above in a different color. Right, so examining this graph right here, this was 3 1/8, 2, 1/4, 1, 1/2, 0, 1, -1, and 2, -2 and 4, -3 and 8. There should have been more of a curve here, but I kind of failed at that. So this right here is f of x is equal to 1/2 raised to the exponent x. And as we can see, it's a mirror reflection of the function f of x is equal to 2x in the y-axis, right? So by taking the reciprocal of this base, 1/2, I've achieved a reflection in the y-axis. As we can see, it also asks us to do the graph of y is equal to 3 to the power of x, and y is equal to 1/3 to the power of x. So what I've done for that is I have plotted it in Desmos, the green graph being y is equal to 3 to the power of x, and y is equal to 1/3 to the power of x. So again, by taking the reciprocal of this base, I've achieved a reflection in the y-axis. And let's look at what these graphs have in common. Well, as we can see right here, the y-intercept is in common right there. And that is 0, 1, right? Because again, anything raised to the power of 0 is going to equal to 1, right? So this 1/3 raised to the power of 0 will be equal to 1. What else do these two graphs have in common? Well, as you can see, they both are asymptotic with y is equal to 0. So they both have the same asymptote. And that right there also is the same asymptote for the graph that we had plotted previously as well. And we can see that also the y-intercepts are the same. So the question asked, what do these graphs have in common and how do they differ? Well, how are they differing? As you can see, y is equal to 3 grows at a much faster rate, whereas y is equal to 1/3 diminishes at a much faster rate. So the shape of them is a little different in terms of the growth, but they have the same asymptote and the same y-intercept. So we're going to include that in our note now. So what do these two have in common? Well, they have the same y-intercept, and they have the same asymptote. How do they differ? Well, they either increase or decrease at different rates, and that was depending on the base. So y is equal to 2x increased at a slower rate than y is equal to 3x. Okay, so if we turn the page, it's asking us to fill in this chart. So f of x is equal to 1/2 x. What is the y-intercept? Well, the y-intercept for there was 0, 1, right? Because again, when x is equal to 0, this will be 1. Does it increase or decrease as x goes towards positive infinity? So with f of x is equal to 1/2 x, well, as x becomes more and more positive, so as it goes to positive infinity, the graph decreases. So right here, I would write that the graph decreases. The domain, as we saw, x is an element of real numbers because it spans all possible values of x. And the range is y is an element of real numbers such that y is greater than 0. Right? Y can never be less than 0 because there is no exponent that will make a number negative. Right? So it's always greater than 0. And there's also no exponent that will make this function equal to 0. Let's take a look at the next graph as well. So f of x is equal to 3 of x. 3 to the power of x. There it is in Desmos. And as we can see here, the y-intercept is the same, 0, 1. So I'll just put these right here to indicate that it's the same. Now, as x goes towards positive infinity, what happens to this graph? Well, as we can see, it increases. And it has the same domain and range as the previous function. So it's going to span all the x values, and it's going to be greater than 0 for the y values. So same and same. Okay, so how is this function going to be different from this one? Well, we said that they're going to have the same y-intercept, right? Because again, when x is equal to 0, this will be equal to 1. And if the base changes from 3 to 10, is it still going to increase as x goes towards positive infinity? Well, let's plot this and see. As we can see, as x goes towards positive infinity, the graph increases. And just as we said on the previous page, it increases at a much faster rate, and that's because the base is now much larger, right? So 10 to the power of 1 is 10, but 10 to the power of 2 is 100, which is much larger than our previous graphs. So this also increases, and it has the same domain and range. Now, this one was a fraction. This one also is a fraction because 0.25 is simply 1 over 4 raised to the exponent of x. Same y-intercept. And if this is a fraction, is it going to increase as x approaches infinity, or is it going to decrease as x approaches infinity? Well, as we saw here, this fraction caused it to decrease as x approaches infinity. We'll see what happens with this one as we graph it. So as we expect, as x approaches positive infinity, the graph decreases. Okay, so this decreases. Same domain and range. I think we can confidently say that this y-intercept will be the same, but that if the base is greater than 1, it's going to increase as x approaches positive infinity, and it will have the same domain and range. So what we're going to do now is we're going to summarize our findings on the base exponential function. So the graph of f of x is equal to b raised to the exponent x is increasing when b is greater than 1. Right? So when the base was greater than 1, the graph increased. It decreased when the base was a fraction. So when b is a fraction, it decreased. And what was the asymptote that we always had? So in each of these graphs, we always had y is equal to 0 as the asymptote for this general function. We saw that the domain and range did not change even though we changed the base. So the domain was x is an element of real numbers, y is an element of real numbers such that y is greater than 0, and the y-intercept never changed either. The y-intercept was consistently 1, right? And that's, as we said before, that when x is equal to 0, the exponent, when x is equal to 0, the exponent is 0, causing the function to equal to 1. There's one restriction that we want to place on here. There are a couple of restrictions. Note, b, your base can't be equal to 1 or 0 because this would not yield a exponential function. Okay. And I want you to think about why that is. There's a homework question to that effect. The last thing that we're going to do is we're going to look at first and second differences for these three functions. So this is y is equal to 2x, so a linear function, a parabolic or quadratic function and the exponential function. And we're going to compare what the first and second difference is like. So I'm going to go ahead and set up a first and second difference column in each of these, and we're going to look at what they yield. Okay, so looking at my first differences for this, making sure that the x values are going up at a constant rate, so 0, 1, 2, 3, that allows me to take my first differences. So 2 minus 0, well, that's 2. 4 minus 2 is 2. 6 minus 4 is 2. So my first differences are all equal to 2. So I would say that my first differences are all constant. And then when I go and do my second differences, 2 minus 2 is 0. 2 minus 2 is 0. So my second differences are 0. For the quadratic function, recalling from last year, my first differences, 1 minus 0 is 1, 4 minus 1 is 3, 9 minus 4 is 5. So my first differences are non-constant. But my second differences, if I look at those, 3 minus 1 is 2, 5 minus 3 is 2. So my second differences are constant. Finally, the exponential function. Doing my first differences, 2 minus 1 is 1, 4 minus 2 is 2, and 8 minus 4 is 4. So I think I can say that these ones are non-constant. Now, my second differences. 2 minus 1 is 1. 4 minus 2 is 2. Also non-constant. But perhaps you may have noticed a pattern here. Look at what we have between these first differences and also between these second differences. Is there a number that we can multiply this first difference to achieve this first difference? So if I take a look, I can multiply this by 2 and I get 2. I can take this first difference and multiply it by 2 and I get 4. What if we added another column here, or rather another value in our column? When x is equal to 4, y is equal to 16, well, that means that that first difference there is going to be 8. And again, we have the same pattern. Same thing with my second differences. 1 times 2 would give me 2. Let's quickly calculate this second difference. 8 minus 4 is 4. So this also follows the same pattern. 2 times 2 is 4. Okay, so here's our summary at the end that will finish off the lesson. Linear functions have first differences, as we saw here, first differences that are constant, and second differences that are equal to 0. Quadratic functions have first differences that are non-constant, first differences that are non-constant, and second differences that are constant. Exponential functions have first and second differences, as you can see here, that are non-constant. However, there is a constant factor between them. So the factor between each of these first differences is a factor of 2. Okay, it's going up by a factor of 2. And what you may have surmised is that, as you can see, the factor is the base of the function, base of the exponential function. Okay. Thanks for watching, and the following page is your homework assignment.